Okay.
Oh,
Okay, so welcome everyone. Thanks for spending your precious night after, I don't know, like going for algo tutorial to go for more algo tutorials. Kind of some nerd shit, but it's okay. Thanks for anyways. So today I'll be presenting on fantastic range query data structures and where to find them. So this is like the highest production quality of this entire set of slides. Literally everything else is black and white. So please admire it. Okay, so what the hell is a range query data structure? So a range query data structure is basically this, right? So I have some types of problems where it's okay, given an array, I want you to find me the sum of numbers in a range like multiple times. So what I mean by that is, okay, let's say I have an array, I have an array A, right? Then I have like A1, A2, A3, blah, 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 until like A400 or something. I'll ask you questions like, okay, give me the sum of elements in the range like 1 to 150. Give me the sum of elements, give me the sum of all the elements in the range 150 to 200, right? So this is what I mean by a range query. So intuitively, there should be like quite a easy way to answer this, right? So like if I ask you, okay, give me the sum of elements in this range, you just write like a quick for loop, then you just sum everything up, and then you give me that as the answer. So that's quite that should be like the basic solution that you guys would know of. But the problem is, what if I ask you to do this for me multiple times, right? So more formally, I have like Q number of queries, and you have to answer all of these Q queries. The total runtime for such a program would be n times Q. So you have nq operations. So this is like the naive runtime, right? And I will claim that you can actually do much better than this if you're a bit smarter about your data structure. And one of the things that allows us to sort of slowly come up with better data structures to answer such queries is just by the observation that there's repeated computation, right? So normally, let's say I want the sum from like 1 to 7. Then I want the sum from like 3 to 8. We notice there's actually like there's actually repeated computation of the queries from like 3, 4, 5, 6, 7. So whenever you see like repeated computation, it should be like a hint that, okay, there's actually some way for you to reuse these previous results to find like a better way to do this. So
at this point, does everyone know like the problem we're trying to solve? It knows pretty fast. Although actually, okay, what's the max ON element in
which one?
max ON element.
Oh, sorry. Okay. Yeah, so basically what I mean by that is, let's say I have an array of size, array A of size n, right? So that means I have A1, A2, so on and so forth. Okay, yeah. Okay, so if this gets a bit too like crazy, just let me know. I will slow down a bit. I genuinely have like no idea how to pace myself because I've never TA'd before. Not like Sean or Cogray. So yeah, okay. So what I mean more formally is let's say I have an array A, then I have n elements in the array. So maybe like it'll be 2, 3, 4, like 100, 102, and in total there are n elements in this. So that Q is like the number of queries that I want to make, where each query is in the form, okay, I want the sum from like give me the sum from like the 10th element to like the 15th element. Okay, so far everyone gets this, right? This is what I mean by range query. So if my array is of size n and I have Q possible, and I ask a query Q times, what is the maximum number of operations that you will do in your program? It will be nq, right? Because I could just ask like the query of elements from like 0 to n like Q times, right? Then you have to do 0 plus 1 plus 2 plus 3 all the way to n, and you have to repeat this Q times. That's why in the worst case, it will be an nq complexity. Does that make sense? Yeah. So this is like so if you just literally just use an array and like that's your program, then yes, this is the best complexity that you'll get, nq. But we want some sort of like data structure that allows us to answer these questions more efficiently, right? So we want some sort of range query data structure which supports these operations. We want a range query, and also in some questions they might also say, given that I update this element at this index to I change it to something else. So if I were to put an actual example here, maybe the question will say, okay, I want to change this to 150. Then what is the new sum of this? Then afterwards continue processing like the range queries as per normal. So some questions might have these kind of like tweaks where they ask you to update certain elements in the range, update certain elements in the array as well. So we might also want to support these kind of operations. So far everyone's following me? Like you kind of get the idea of what a range query data structure is, all that? Yeah, okay. So in this talk, range query data structures that you probably won't really see in CS 2040S. In terms of like things you'll be most likely to see, prefix sum will probably be, appear in like almost like half your lead codes or something, like half of your lead codes or something. Segment trees, if like you're a bigger nerd and you do like code forces, maybe you'll use at some point. Sparse table, you'll literally never see it probably. Square root decomposition, you'll literally never see it. These two I'll cover if I have a bit more time, but I just put them in because I thought they're cool and interesting. I'm kind of lazy to find a good implementation, but hopefully by the end of the talk, you should kind of get the idea of how to actually implement these data structures yourself. I want to bring across like the essence of how these data structures work. So I don't know what the difficulty is. I thought it would be roughly CS 2040S plus maybe. Then for this crowd of people, you know who you are. So you probably will know this like intuitively or whatever, but I sort of like formalized it in a kind of mathy way, so maybe that will help as well. I don't know, maybe it's something fresh. Okay, so let's start off with our simplest range query data structure, which is a prefix sum. I think Sean actually covered this in a previous episode, in a previous session of Orca code. So yeah, let me just cover it again. So basically, well, prefix sum is basically this idea that for a given array A, compute an auxiliary array B, blah blah blah, bunch of words. Let me just show you what an actual example. So let's say my array A is okay, my array A is 1, 4, 7, 2, 8, right? Then my array B, the first element will be 1. The second element will be 1 plus 4, which is 5. The third element will be 1 plus 4 plus 7, which is 12. After that is 14. Then after that is 22, yeah. So you'll get what the array B is. It's basically just like the sums that's starting from the start. The prefix sums are basically. So this is what they say, or this is what they call a prefix sum array, where it's basically you just take, okay, each element corresponds to like the sum of all the elements up to there. And the reason why we do this is so that actually once we have this, right, we can actually use this to we can actually use this to actually answer our range queries like quite effectively, right? So okay, if I ask you, okay, give me the sum of all elements from 0 to 25, then the answer to that is literally just B25, right? Give me the sum of all elements from 0 to 100, then the answer to that is literally just B100. That so far it makes sense? So what if I ask you, okay, give me the sum of all elements from 25 to 100? So everything makes sense so far, right? Okay, so give me the sum of elements from 25 to 100. At first, you might think, okay, wait, then this is not what I calculated, right? There's no way for me to use my answer to do this. But actually, all I have to do is just take B100 minus B25. Does this make sense? Right? So if we actually calculate this array B, and this takes O(n) time, it actually allows us to answer range queries in O1. Previously, what we had to do was, given a range query, right, we actually had to add up every single element one by one, right? So if I wanted 25 to 100, I had to add 25, 26, 27, 28, 29, blah, 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 all the way to 100. But in this case, because I've already computed the sums from like 0 to 100, 0 to 25, all I have to do is literally just take the first sum minus the second sum to give you the answer. So we've already found like, this is like the simplest data structure, and it allows you to actually answer these queries in like a much faster time. We went from like having to add every single thing up to just literally answering it like in O1 time. So far, everyone, this makes sense to everyone? So yeah, so this is basically what a prefix sum is. So far I've been talking about like sums, right? But what other operations are actually possible? So okay, Scott, Gory, what's your vibes?
What are the vibes?
Can I go through this slide or? Okay, so
Go ahead.
okay, I'll just go through like the operations that will be a bit more familiar. So maybe let's say just now we had like what we call range, like sum queries, right? We wanted you to find the sum of all elements in a range. So what if maybe I change the question a bit? I want to find the product of all the elements in the range, right? So would that still be possible? It'll still be possible, right? Because all I have to do is just like, okay, maybe now I have okay, I cannot calculate so many products, but 7, 5, 2. So like now instead of calculating like the sum from 0 to 5, I'll calculate like the product from 0 to 5. Then I take the product from 0 to 5 divided by the product from 0 to 2. Then this gives me like the sum from this gives me the product from 3 to 5. Does this make sense so far? So this is another type of operation that that I can actually support with this prefix sum. Another type of operation I can actually support is this thing called like a matrix addition. So same, I mean, if you can support regular addition, you should be able to support matrix addition, right? Like there's not that much difference. It's just the same thing, but you do it with a matrix instead. What about matrix multiplication? Can I do that? So the answer to that is in general, no. But if you have like if you limit it to matrices that are like they have non-zero determinant. So what I mean by that is you can find the inverse for the matrix for any any matrix in there, then the answer is yes. So now the more interesting question is, okay, can I use this to support minimum and maximum range queries? Like, can this technique work for minimum to maximum range queries? So what I mean by that is, what is a minimum range query? So given like an array 0, 2, 3, 5, 7, 8, okay, I want like the minimum of this range. So the minimum for this range would be 2. Or I want the minimum for this range. Then the minimum for this range would be 3. Right, so you'll get the idea of what a minimum range query is. Can I use this technique to answer these kind of questions?
Not. I guess in this specific example, can you do it? Oh, it looks like you can, right? Okay. But then what if the array isn't increasing? Right, so let's say we have.
Let's say I have something like 3, 2, 7, 1, 5, 2. So maybe I'll go through the step by step. So what we did just now was, first we calculated like okay, let's say we calculate the minimum from this to this, the minimum from this to this, minimum from this to this, so on and so forth, right? This is what we have. And maybe our answers to that would be, this would be 3, and this would be 2, this would be 7, this is 1. Sorry, I can't count for shit. This is 2, this is 1, this is 1, this is 1. So the idea just now was, in order to find the minimum, in order to find the answer from like 3 to 5, we took the answer from 5 and we sort of like we minus away the answer from 3. This is the idea of what we did just now, correct? Can we do that with if what we computed is like the minimum of the range from 0 to n? Not really, right? Because you can't like invert the operation, right? In the case of addition just now, you could just take this thing minus away that thing. You could undo that. You could undo like the effects of adding from like 0 to 3, right? In the case of multiplication, you could take the product divided by another product. You could undo the effects of actually multiplying by that product. So this technique only works if you have what I call as an inverse. You need to be able to like undo the operation. So far, does that make sense? Okay, yeah. So basically, ignore these two lines. The idea is just this: you need to be able to find like the inverse of like this. You need to be able to find the inverse of that in order to use prefix sums to speed up your range queries. So there are some like prefix sum problems. It's a reference implementation, but I won't really go into that lah. Okay, so we wanted some sort of range query data structure which supported these two operations with range query and point updates and range updates. So far, we've seen that prefix sum allows us to get range queries in prefix sums allows us to get range queries in O1 time, right? But what about point updates? So what I mean by that is, so let's say just now we had an array 3, 4, 7, 2, 1, 10, right? Then at any given point in time, I can tell you, okay, I want to change the element here to maybe like 42, right? Then I want you to continue giving me like the sum of all the elements in any range that I ask for. In this case, if we're doing it naively, right, where we basically just add everything up and then we give you the answer, this doesn't really add too much of a challenge, right? It's literally just replacing the element in the array and then like still computing it as before, correct? That makes sense, right? So in the naive way, this is still ONQ. But if let's say we did prefix sums, right? So we have the array B. So maybe just now B was this is 7, this is 2. So maybe just now B was like this, right? 9, then this is 11, this is 13, this is 23. If we change, let's say this to 42, right? It actually forces us to actually recalculate all of these values as well. Does this make sense? So in the case of a prefix sum, updates actually take ON time. So if let's say we have Q possible queries, and of these Q queries, all of these are just like updates, right? Our overall runtime is still ONQ. Does this make sense? Because if we have Q possible queries and every single query is, let's say, just keep changing the first element, right? It forces us to keep recalculating this prefix sum over and over again. And each time we recalculate the prefix sum, it's like n operations. And then we do Q times of these recalculations. So it's NQ overall. So with prefix sums, we actually don't get better efficiency in terms of update operations. Yeah, sure, we get better efficiency when it comes to range queries, but our update operations are still like as inefficient as before. So, and furthermore, there's the prefix sums actually require like a bit more structure from your operations, right? Because we needed to be able to find like the inverse of an operation. But this kind of structure may not exist for all types of like functions or operations that we want to do. Like I showed you just now, minimum when you find a minimum of something like of a range, right? There's not like an easy way to sort of take out a range, right? There's not an easy way to sort of undo like finding the minimum of something, right? Sums have it, products have it, some other random types of operations have it, but in this case, minimum or maximum did not have it. So we were unable to use this technique to speed up what we call as range minimum queries or range maximum queries, right? So now it brings us, so with that in mind, I bring you to like the central topic of today's talk, which is basically just segment trees. So segment trees is like something that you probably have heard of at some point if you do a bit of algos. If you're like a giga nerd that does like NOI or something like that, then you'll probably use these a lot. Yeah. So what I promise to you is this. With this special data structure, you'll be able to get a good time complexity for range queries. In fact, you'll be able to get O-log-n. Okay, this is still worse than the prefix sums time complexity of O1. But we get but this allows us to get a lot of other benefits as well, right? Updates we're able to do updates in log-n with segment trees. And at the same time, we're also able to support more types of operations. So you know how just now I said with prefix sums, we could not support like range minimum queries or range maximum queries? Well, it turns out with segment trees, we actually can support these kind of queries. So with that in mind, these are all the promises I give to you. So what the hell actually is a segment tree? Let's see how we can actually derive one. This is a horrible slide. I should have not written so many words, but yeah, okay. Basically, for the rest of the talk, right, because I want to for the rest of the talk, when I talk about ranges, I will just be writing them in shorthand as like this, right? So this denotes like the range from 0 to 4. 0. This denotes the range 0, 1, 2, 3. So 0 is included, 4 is excluded. There's a reason why I do this, but basically, long story short, it makes like working with ranges a lot more intuitive. You save a lot, like you don't get as many random like off by one errors. But let's just say that this is a convention for the rest of this talk. Then, given already computed sums of like, let's say 0 to 16, this means that it's the sum from like the sum of 0, 1, 2, 3, ... all the way up to 16. This is the sum of like 0, 1, 2, 3, ... 8. Given all of these blocks, right, can I find a way to minimize the amount of blocks I use to compute a range? So a bunch of words, a bunch of nonsense. Maybe I'll just show you a picture and it makes more sense. Okay, so let's say this is my original array. This is my original array A, right? 3, 4, 2, 9, 1, 4, 2, 5. At the same time, I also have more like these like blocks which I've already computed. So I have this block going from 0 to 2. This represents the sum of these blocks, the sum of these two elements. I have this block 11, which represents the sum of these two elements. I have this block 5, represents the sum of these, so on and so forth. And then I also have like the bigger blocks. So these are length 4 blocks. 18 represents the sum of all these elements. 12 represents the sum of all these elements. And I have the biggest block, which is 30, and it represents the sum of everything. Okay, so you kind of get what I mean by we have all of these like pre-computed blocks, right? So let's see. Okay, so suppose I have this already pre-computed for you. How would I actually be able to answer a range query in a more effective way? Okay, so let's say you have all of these blocks to play with. I ask you to give me the, sorry, let me just label all of these so it's easier for me to see. I ask you to give me the sum of elements from 1 to 5. Okay, so yeah, sum of elements from 1 to 5. This is 6 exclusive, so it's this range. So what you could do is this, okay? I can take 4, I can use all of these blocks. I take 4 plus 2 plus 9 plus 1 plus 4, right? So that's what? 6, 15, 16, 20. Okay, yeah, so it's 20. But, so the challenge is, I want you to give me this sum using as few blocks as possible. So how would you use fewer blocks, like fewer blocks than just now? Does the idea of the game that I'm trying to play make sense here? Yeah, so these 3 blocks are right. So the idea of a segment tree is basically this. You have this like nice you have computed all of these like nice blocks of different lengths. You can use these blocks to minimize the amount of computations that you have to do, right? Does that kind of make sense? So maybe I run through a few more examples. Okay, maybe I want the sum of elements from like 3 to 7, for instance. Then I'll use this block and this block. Make sense? If I want the sum of elements from 3 to 6, 3 to 7, now I'll use this block, I'll use this block, and I'll use this block. Make sense so far? And actually what you'll notice is, if I break my computation up into like these different blocks and I try to minimize the amount of blocks I use at any given time, I actually use only like 3 blocks, right? Like you can't, okay, maybe I use at most 4 blocks. You can't really find an array, you can't really find like a range that you have to use like more than 4 blocks to compute. Does that make sense? Like let's try, okay? Like maybe I want I try to find a range that uses more than 4 blocks to compute. So maybe I want okay, 1 to 8, right? I definitely have to use this one. I have to use this one. Okay, I have to use this one. I have to use this one. Okay, 4 blocks. If I want 1 to 7, I use this block, use this block, use this block, I use this block. It's still 4, right? So no matter what range I want to compute, right? If I use these blocks and I use the minimum amount of blocks possible, actually I can get away with just doing 4 computations, right? So it's more efficient than having to add everything up one by one. So that's basically the essence of what a segment tree is you pre-compute all of these like big blocks, and then afterwards you try to break down your computation using all of these big blocks. I forgot what's the next slide. Okay, yeah. Yeah. So maybe let's try to think about how we might try to do this process of minimizing the amount of blocks we have to use algorithmically, right? So, okay, I have 2 to 7, right? I want the sum of all elements from 2 excluding 7. So maybe let's start at the top. Okay, this is the block that represents all of these elements, right? And this is actually much bigger than what we're interested in, right? We are basically only interested in this part. So in a sense, it's kind of useless for us, right? Because we cannot use, we can't really use this sum to do anything. It's too big, it's too broad. So, okay, if we cannot use this sum to do anything, let's try to go to the smaller blocks. Okay, let's say I use these blocks and these blocks. We still can't use these blocks to do anything, right? Because they're still too big. They include elements that are outside of what we actually want. Okay, so let's go down further to another level. Let's look at these 4 blocks. Okay. And now we have a situation where, because these 2 blocks are actually completely contained within the range that we want, right? We can actually use these 2 blocks to do our computation. And further, yeah, so we can actually use these 2 blocks to do our computation. So we know that the range that we want is actually like 15 plus 5 plus some other stuff. Oops. So okay, with that in mind, we don't have to like go down any further because we've already realized that we can use these two blocks completely. But we still have like these two like blocks over here that we still have to consider. Okay. So now we're at this block, right? Let's say this block number 7 here. We realize that it's completely useless for us because it represents a sum that's outside of the range that we're interested in. It represents the sum of these two elements, but we're only interested in the sum of all these elements. So we can just ignore it, right? Whereas in this, then we look at this side here. This side is still like too big because it includes stuff that we don't care about. So we actually have to break it down even further. We have to go even finer. So now we're interested in these two. Then, okay, this is completely contained within the range that we want. So we include this in. And in the case of the other one, it's completely outside. We don't give a shit about it, right? So if you think about breaking down your operations like this, you start to see like hints of how you might be able to do this algorithmically, right? So let me phrase it in let me go to the next slide where I try to phrase it more algorithmically. So so a node is a struct that contains 5 values, all these things. Basically, what I mean by that is a node is like a sort of it's an object that has these things. First, the node has the left end of the range that it represents, and then it has the right end of the range that it represents. A node also has the sum of all of the elements in that range. A node also points to like its two smaller blocks, right? So in this case, you have the block 0, 8, which can be further subdivided into the blocks 0, 4 and 4, 8. Does this make sense so far? Yeah. So sum would actually be a function. So sum ij node is a function that, given a range ij, returns you the sum of all the points in the node's range which intersect with it. Bunch of words. Let's see what I actually mean with an example. So let's say I have a node n. It represents the sum of all elements from 0 to 7. So this is A0 plus A1 plus ... all the way to A7, right? And let's say I call this function sum 2, 10, n. So what this means is that I want all of the okay, so ideally what I want is this sum A2 plus A3 plus ... all the way until A9, right? But if you cannot give me all of the elements that I'm requesting for, it's okay. Just give me all of the elements that you already have. So in this case, calling sum 2, 10, n will actually give me the answer, will actually give me this sum, which is 2 plus A3 plus ... all the way until A7. Does this make sense? So it's a function that, given a range, returns you the sum of all points in the node's range which intersect with it. And the thing about that is that you'll notice is that if let's say if let's say this is the sum, this is the node that I call this function on, right? If I call 2, 7 on it, it should actually return me the answer to my range query, right? So at the start, the whole thing I was trying to do was that I was trying to design a data structure to give me answers to any arbitrary range query, right? And let's say I have defined this function sum that, given a node, returns me the sum of all of the points in the node's range which intersect with it. So if I have a node that represents the entire damn range, and I call sum maybe like 2, 7 on it, it should give me all of the nodes which intersect with the entire range, which is just literally 2, 7, right? So this is the node represents this sum. I want the range. I actually want this like range. And then it'll return me the intersection of these two ranges. So it'll return me the sum of everything here, which is just the answer that I want. Okay. So if I can define this sum operation, if I can define this like sum function on this tree, it actually allows me to just get range queries already. So phrasing it algorithmically, sum ij is equals to the sum ij of the left child and the right child. Okay. So if let's say I want the sum from from 2 to 7 here, and I call it on this node, it's actually the same as the sum of the operation of sum 2, 7 on this node plus the sum 2, 7 on the right node. Does this make sense so far? Yeah. And because it's recursive, you kind of have to start thinking about like, okay, when does this actually terminate, right? So earlier we saw hints of when we actually have to stop calculating. So earlier just now when let's say we had we were interested in, what do you say? Okay, let's say we're interested in this range. When we were calculating on this node, right? We broke it down into two further subcases. We wanted the sum on the left side and the sum on the right side. We noticed that the sum on the left side is actually completely disjoint from like the range that we're actually interested in. So in that case, we can just terminate there because we know that we don't have to consider any of the we don't have to consider anything else on this side anymore. It contributes nothing to the sum that we actually want. So in this case, we terminated and we just return 0. And the other case was on the right side, right? On the right side, the range that represents is actually completely within the sum that we want, right? So we actually don't have to break it down further. We can literally just return this, right? Because it just so happens that this block which represents the sum from like 2 to 3 is also like the block that we're actually interested in, right? This is the answer to the query that we want. So this hints at the two base cases you need for this recursion. One is that it's completely disjoint, right? This is completely disjoint from the sum from the range that we want. Or two, it's completely contained within the range that we want. Does this make sense? So if that's not the case, right? If let's say it's neither completely contained nor it's completely disjoint, that means that there's some intersection with the range that we want. So in those cases, we actually have to break it down even further, right? Because like so in cases like that, where, okay, let's say, what's an example of this, where the range is not completely contained, but it also has some intersection. Okay, let's say I want the sum of all the elements in this range. And let's say I'm here at the big node originally. This big node is not completely contained, but it's also not disjoint, right? Because it intersects all of these elements. So this is too coarse for us. We have to go like a bit finer. We have to look at some smaller blocks. So we break it down further. Now we look at these two blocks. Okay, this block represents the elements here, and this block represents the elements here. In the case of the right side, this block is actually completely contained within the range that we want, right? Remember, this is the range that we want, and we notice that this is actually completely contained within the range that we want. So we just return the sum here, right? We just return 12 here. And then on the case of the left side, we have a similar issue where it's neither completely contained, nor is it completely disjoint. So we break it down even further. So now we consider these two blocks, okay? We consider the block with number 7 with like a sum of 7. We see that now in this case, it's completely disjoint from the range that we're actually interested in, right? Because this is the range we're interested in. So we just ignore it. Like we just return 0. We know that it contributes nothing to the sum that we actually want. Then on the case of the right side, well, we see that it's completely contained within the range that we want. So we just return 11. So the sum to the answer to the sum of elements for this entire part is literally just 11 plus 12. Does that make sense? So like I yapped a lot about how I want to actually break down the computation, but I could just show you like the algorithm for actually how to actually implement a segment tree. But this is how you sort of like this is how to sort of reason about like how you will actually derive a segment tree from scratch, which is basically first you have all of these blocks, right? You try to break down your computation using as few blocks as can, and you notice that actually there's a nice elegant way to do it with a bit of recursion. Then you think about it, okay, these are the base cases for my recursion. So If the block is completely contained, okay, I add it to my sum. If the block is completely disjoint, I don't give a shit because it contributes nothing to my sum. If the block has some intersection with the sum that the range I'm actually interested in, I have to use a finer block. I have to look at some finer blocks. So that's kind of the idea that I want to bring across. Yeah, so basically what I wrote on this slide now. So first, sum has a recursive structure. Then the base cases of this recursive structure, if the node is fully contained within, just return the sum. If the node is fully disjoint, return 0. Otherwise, as intersection, you need to look at the finer blocks. So yeah, originally the intention of this slide was to kind of so I've given you like the definition for what the algorithm should be doing on the previous slide. Now I wanted to work through like the what I actually be doing on this what the algorithm actually does on this slide. So I feel like I've basically been doing that. So maybe I'll just, I don't know, are you comfortable with what I've been saying so far? I can step through the algorithm, sort of give you an idea to sort of maybe get a better sense of what I'm saying this algorithm does. Hmm? Okay, so maybe I'll just step through it. I'm interested in the sum from 0, 2 to, I'm gonna label this first. 0, 1, 2, 3, 4, 5, 6, 7. I'm interested in the sum from 1 to 6, for instance. Yeah. So what I do is I call sum 1 to 6 on this node. So sum 1 to 6 on this node, and this node represents 0 to 8. I see that this node, like 0 to 8 is not fully contained within 1 to 6, right? So it's too big for us. So we actually have to recur, we have to break it down into smaller blocks. We recurse onto its children. So now let's go into its children. Okay, I call sum 1 to 6 on the block representing 1 to on the block representing 0 to 4. Similar issue. This is 1 to 6. This is the block that I'm interested in. Like the green represents the range I'm interested in. Red represents the range that the block actually represents. So again, similar issue of it's neither fully contained within or it's disjoint. So I have to go down even further. Okay. Now I break it down further. Sum 1 to 6 here. Sum 1 to 6 here. So on the left, similar situation. I have to go further, but at this point you should kind of know like what the final output for the one on the left is going to be. I'll break it down further. Then afterwards, I will terminate here at this block which is fully contained, and then I'll feed the answers back up. So this will be 4, and then this will give me 4. Then okay, and then I continue with the rest of the recursion. So in this case, this node which represents the range here to here is fully contained within the green range, right? Red range is fully contained within the green range. That means that's great. I don't have to continue. I don't have to break it down even further. I can use the block. I can use the sum that I have in this range, 11. Okay. So now let's continue on the right side of this entire thing. So I call the sum operation on this. I notice that the red range is this, right? Red range is not fully contained within green range. I break it down even further. I go into the 2 children here. Oh, okay. This range is fully contained. That's great. I return 5. Then in this case, range is not fully contained. I break it down into its children. Oh, this is fully contained. I return 2. This one is not full. This one is completely disjoint. So I just return 0. So the answer to this is 7. Then when I return these two, so now I've completed the computations for the left side and the right side. I can finally return. Left side gives me 11. Right side gives me 7. Total, I get 18. Am I stupid? It's not this, clearly not 18. Sorry. My bad. I forgot that this side is actually this is it doesn't return 18 here. It's 15. Okay, yeah, now it's 22. Yeah. So this is the idea of how to sum the blocks up in the segment tree. Yeah. Okay. So my claim is that this is like you do range queries in O log n. So what I mean by that is, even though at each step we kind of have this process of, okay, at a node we might have to call the operation on its two smaller children nodes, so on and so forth, right? So in the worst case scenario, we can imagine something like this happening, right? Where, okay, maybe I call sum on this node, then it forces me to go down even further. I call sum on here, I call sum on here, and it forces me to go down even further, right? It sort of looks like doubles at each point. If you just look at it like without really considering it, it might look like there is some case where we have to call sum on every single node, right? But actually, that's not the case. I guarantee you that at every single level, right? So what I mean by level is like this. So this is one level, this is another level of nodes. This is one level of nodes. There's only four operations. And max 4 operations. So let's say I'm looking at the computation for this level. Okay, sorry. I'm looking at the computation for this level. So there's only 4 operations because at any level, you can only have these situations happening. So either I have, okay, sorry, let me think about this. Yeah, at each level, you only have 4 operations because there's only 4 possible ways that you can break up your computation, right? So you can think of it as like this. Okay, number one way is I just use I use both blocks, right? So at that point, I don't have to break it out any further. I can just return up. So that means that at this level, there's only 2 operations. Or the other situation is, okay, maybe my computation is like this. I have to use half of a block. I can use this full block. I can use this full block. So then there will only be 3 operations at a level, right? Or the worst case is, let's say I have to use half of a block. I have to use this full block. I have to use this full block, and I have to use half of a block. Then there will be 4 operations at a single level. Not the best explanation. Let me think of if there's a better way to explain this. Yeah. Yeah, basically, long story short, what I want to say is that range queries, even though the recursion may make it seem like I have to touch every single node, I only have to touch like at most log n nodes. So that's why the overall complexity of a range query is log n, because I only have to like consider log n blocks at most. Yeah. So far, we've been doing calculations with the assumption that the blocks were already computed for us. So how do we actually compute the blocks in the first place? So I can do it like very naively, right? So I know that these are all the blocks that I need to compute, right? So maybe this is 2, 7, 4, 5, 6, 1, 5, 2. I can literally just go through every single block. Okay. Maybe I need to calculate the sum for the block that represents 0 to 8. I take 2 plus 7 plus 4 plus 5 plus 6 plus blah 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 all the way until 2. So I have to add everything up. I don't know what the answer for that is. What's this? 9, 13, 18, 24, 25, 30, 32, right? Then I repeat for every single block here. I have to do 2 plus 7 plus 4 plus 5. That's 9, that's 13, that's 18. Then this is 6 plus 1 plus 5 plus 2. That is 14. Yeah. Then I repeat down over and over again. I just keep calculating. So if I do it like this, which I will call it as like if I calculate the blocks naively, it gives me overall like the number of operations I'll do is n log n, right? Because there are log n levels, but each block for each level I have to add like at least n things, right? So here I have to add 0. I have to add 0 all the way to 8. Then here I have to add here I have to add 0, 1, 2, 3, 4, 4, 5, 6, 7. Each level I have 8 operations. Then I have 4 levels. So I have a total of 32 operations. Yeah. So this is n log n complexity. But actually, what we can do is we can just reuse previously calculated results. So what I mean by that is, rather than building it from the top to bottom, we build it from the bottom to the top. So we go, so this is the array that we have already. We build it upwards. So 2 plus 7, that's 9. 4 plus 5, that's 9. 6 plus 1, that's 7. 5 plus 2, that's 7. In other words, instead of having to calculate everything, we just reuse our two results here, right? This is 18, then 7 plus 7 is 14. Then we just reuse our results and we can get 32 here.
You don't learn like heaps or priority queues and then people use that as this is like similar to your ON. The same person.
Oh shit, yeah.
No, right. Probably hit the button number.
But I stop this thing. And I just turn off the thing. Maybe that stops it.
So people already know what's in the
Nice. Oh shit, nice. All right. So previously we considered updates, right? We updated the prefix sums that took like ON operations. So now let's say, okay, we want to update this block to maybe, I don't know, 2. Can we think of what we actually have to change in here? Previously, when we did prefix sums, we have to change every single prefix sum from that point onwards, right? But in this case, all we have to change are just these blocks. We have to change this to 3, we have to change this to 10, and we have to change this to 28. We only modified 4 blocks in total. And if you think about it, yeah, for any point update, we only have to modify 4 blocks, right? Because there's only 4 possible blocks that contains it, right? So let's say rather than modify that one, let's say I want to change this one. Okay, I change this to 5. Okay, what blocks I have to modify? I have to modify this one, change it to 13. Then I have to modify this one, I change it to 20. I modify this one, I change it to 32. Am I able to count? I cannot count. This is 14, this is 21, and this is 33. Yes, sorry. Yeah. And you notice that at every single point, like if I want to recalculate, it's actually quite simple, right? I just use the answer on the right. I use what I've already calculated, and then I add it with like what I've changed. So I just keep propagating the update upwards. So yeah, updates are in log n now as well. Just now updates were on, now updates were log n. Oh, I added this slide for myself to use, but I didn't even use it in the end. So reference implementation, okay, maybe I ignore this slide first. Yeah. So with all these ideas that I brought across, hopefully you would be able to implement like your own data structure, like your own segment tree. So the idea is try to represent these blocks, try to represent like this tree of blocks, and then afterwards write your write the function so that it terminates correctly and it uses like the children correctly. You could probably make like a lead code question with this, I guess. Yeah. So okay, let's recap. We wanted some sort of range query data structure which supported these operations as fast as possible. First is a range query of log n. Second is a point update of log n. We've achieved these two. First we wanted a range update. First we wanted a range query, and secondly we wanted a point update. We've achieved these two goals, right? We've gotten log n time for both of these. But what if we wanted to update things in a range, right? So earlier what we've been doing is we only change one element at a time. I change this to 7, or maybe I change another element at a time. I change it to 10. What if, let's say, I want to change an entire range of elements at a time? Rather than changing only one element, maybe now I want to say, okay, within this range, I change everything. I add 2 to everything. This is 4, this is 11, this is 3, and this is 6. Right, yeah. So there's a simple way to sort of use this segment tree that we've just made and to support these, like what we call as range updates. And that's literally to just apply the update for every single element in the range that we want to update, right? So if I want to update all of these in a range, it's the same thing as, okay, first I update this one, then I update this one, then I update this one, then I update this one. Okay. But the problem with that now is if every single update is log n, right? And my range is maybe let's say n. My range is n. Every single update is log n. So to apply this operation where I basically add 2 to the entire range, it will take me n log n time, right? Just to do this one operation, which is just add 2 to every single number in the range. Because I have to update the data structure and everything. So this might seem like the best that we can do, right? But actually, we can do even better. If we optimize this even further, we add another tweak, we can actually achieve arbitrary range updates in O log n. Yeah. So this is probably like this will be like, I guess the most abstract part of the talk, maybe lazy propagation. So our data structure doesn't support efficient range updates. I claim that if I further modify this segment tree, it will be able to support efficient range updates. With that in mind, okay, let's get started on lazy propagation. Okay, so similar to how we broke up computation into blocks, right? Maybe let's try to break up our updates into blocks. Okay, so we store a variable aggregate add, which indicates the aggregate add that should be applied to it. So what I mean by that is if I want to add 1 to a range 0 to 8, then the aggregate add variable for the range should be 1. Can we derive how this should work? So what is written on my side is quite abstract. Let me draw it out. So if I want to add, let's say I want to add 2, right, to the entire range 0 to 8. What I want this to be represented as, the way I want this to be represented in my data structure is basically just a value 2 here. Does this make sense? Because this is my node representing 0 to 8. And I want to add 2 to this entire range. So if I have just one number which represents like if I break up my update into blocks, right? Essentially what I should do is literally just have a 2 for this node here. That's a very clunky way to explain. Do you also get what I mean by here? Get what I mean? Like
Yes.
sorry, let me just drink some water. Like range update or regular updates? Okay, so range update is okay. So just now, let's say I have a point update, right? Yeah, point update is I just change this to 7, maybe. Okay, so let's say I point update something. I add 3 to the element, right? So this becomes 7. Then I propagate the answer upwards. This is what? This is 15. And this is I actually cannot do math. 33. Yeah. So this is what I mean by point update. This makes sense, right? Range updates is basically treated the same, but it's just that instead of adding things in like at a point at a time, I add things in a range instead. So what I mean by that is I apply to an entire range. So now I want to range update this range. So I add 3 to everything here. Does that make sense? Okay. So just now what we did was we broke up the sum into these blocks, right? So what if we can do the same with updates? Rather than updating it point by point, we update the entire blocks by themselves. So that's the question I posed to you. And that's also basically literally what lazy propagation is. So lazy propagation is basically this idea of rather than apply the updates like point by point, right? I apply it to the entire node instead. Okay. So usually when you go online and search for lazy propagation, it's going to be a lot of like either it's like it's a poorly written tutorial, or they just give you the code and they don't really explain to you like how the hell it even works. So I'm going to try to do this thing where, okay, I say that this is what I want to do, and let's try to derive how lazy propagation should work. Okay, so okay, let's say now I say, okay, I want to update all of the elements from 0 to 8 by 2. I want to add 2 to every single element here. And just now I introduced this thing called an aggregate add variable, right? And this is like if sum represents the sum of all the elements from 0 to 8, aggregate add should represent like the update that I want to apply to all of the elements in the sum. So in this case, the aggregate add for this node should be 2. Does this make sense so far? Okay, then now let's say I call, so after I do this update, right? I query for all the sum of all elements from 0 to 8. The way we would have done it just now is, okay, since it's 0 to 8, I call it on the big one, and then, wow, okay, it's literally just contained inside it, right? Because I'm querying for 0 to 8, and just nice, this range represents 0 to 8. So I don't actually have to do any further computation. I can literally just return it. So I return 30. But there's an issue here, right? Just now, I added 2 to every single element in the range. But then now, when I ask for the sum of all the elements in the range, I return 30. I haven't updated the sum to take into account the addition, like the update that I've made. So this brings us to the first thing that we have to consider when implementing lazy propagation. First,
so sorry. Let's split this room into half, like the normal offline process. So I think if you want to listen to the segment 3, like kind of tutorial, you can kind of shift to the front. Then we'll do like half of this way. So the people who know what segment 3s are, or like are interested in other problems, or like cannot follow whatever, then you can come to the back. Then we'll do like normal offline process. Go near Conrad, like just sit at the front if you wanna learn about segment 3s. If you know what segment 3s are, or I guess if you want easier problems with any people, you can come to the back. I guess at the end of like basic segment.
Sorry?
There'll be like basic segment 3 problems at the end.
In my slides or what?
I don't know, at the end of this.
Yeah, sure, I guess. I mean,
we're not. I guess yeah, we're gonna become more open book. There's no key, I guess.
Wait, do you miss a lot just now, Hikaru? You went to the washroom, right?
The aggregated thing.
Okay,
I kind of grasped everything before that.
okay, can.
I don't know how the
Yeah, so to recap, basically I wanted okay, now I want to support this operation called range updates. And similar to how just now I broke up computation into blocks, right? Now I want to try to apply these updates to entire blocks at a time. So the way I do that is, if let's say I have a sum that represents the sum of all the elements in this range, now I have a new variable called aggregate add, which represents like the update I want to do to entire range. So if update 0 to 8 is 2, right? Then this node which represents the range 0 to 8 should have 2. Does this make sense? As in just so the way I'm doing this is, okay, I say that I want to break up updates into blocks. Then I'll try to derive how this entire thing should work. Do you follow so far?
So you add everything below the node.
Yeah, so this is the operation I want to do. So on some level, this is basically the operation I want to do. Basically, I add everything by 2. But I'm trying to find like a more efficient way to do this. And in order to do that, I'm trying to derive how I might do this more efficiently. So like it's trying to show you like the process of how you can actually derive this technique, which we call lazy propagation. So, okay, I call update 082. That means that I want to add 2 to every single element in the range 0 to 8. Okay, so if I have another variable which represents like the update I want to do to a range, in this case, I call my variable aggregate add, right? The variable here, aggregate add, would be 2. Make sense? So, okay, now I'll continue the derivation. So, okay, I call update 082. Then, because I have a node which completely represents that range, then that's good, right? Like I just set that aggregate add to 2. So now, sorry. Now let's say I say, okay, query 08. So if I just call query 08, like and what I did just now, what will happen is actually this. So I call query 08, I call it on the top node. I noticed that actually the top node completely contains the query that I want. So wow, okay, great. I don't have to recurse any further. I just give you the answer. And the answer is 30. But something's wrong here, right? Because I've added 2 to every single element in the range. but then I still give you the old sum of 30, right? So clearly, like so after you do an aggregate add, you need to when you call sum on it afterwards, you need to figure out how this sum actually, like this actually affects the sum. Does that make sense? So in this case, okay, if I add 2 to every single thing in the sum, and so if I have an aggregate 2 on this node, which is basically just adding 2 to everything in the sum, how does that actually affect my actual sum when I try to query for it again? Yeah, literally that's it. So you need to define how you need to be aware of how aggregate sum will interact with the aggregate add will interact with the sum. And the way this modifies our code is actually like this. So in the future, right, whenever we call the sum operation, we actually need to add the aggregate add back into the sum, then we return that. Does that make sense? So let's say I call update 082. So this changes the aggregate add of this node to 2. When I call query 08, I actually need to be aware of the aggregate add. If there's an aggregate add, I need to add it into the sum, then I need to return it. Make sense? So, okay, let's say, okay, so now I call query 08. So since query 08 has been done, okay, so now I'm aware that I actually need to modify the sum to take in note of this aggregate add. So, okay, 30 plus 2 times 8, that's what? 46. Okay, that's nice. So now in the future, whenever I call query 08, it'll give me the correct answer. Okay, so let's continue with the sequence of operations. Okay, now I call query 04. Okay, I call query 04 on this. It's too big, so I go on to its 2 smaller children. The one on the right is like completely useless because it doesn't contain what we want. Then we look at the one on the left. Oh, the one on the left is completely contained within the range that we want. So we return 18. Then we return 18 again. But this is another problem, right? Because we added 2 to every single thing. Every single element in this range has 2 added to it. But we're still returning the old answer of 18. Right? So what was the issue just now? The issue was that when we added the aggregate add back into the sum, right? We actually did not, like, we in a way, we kind of just like ignored its effects on its 2 smaller children. Right? But you cannot just ignore it, one, because if you apply if you apply aggregate sum to the entire range, actually the 2 children will be affected as well, right? So nice. What is going on? My iPad ran out of battery. Bruh. You got a charger?
I have.
Can I borrow a charger? It is so tough, dude. Okay, I guess 5-minute break while I get my iPad charged.
X4 and XXL is self-XL. So remember how if you XOR by itself, right? If you XOR itself, that's like the inverse operation. So if you have, let's say, I don't want to use action numbers because I don't want to use right. If I let's say to find the X of this and then I can do the XOR first, then I update it, then I just update this guy. So because A1 XOR A1, this becomes here. And zero X guy X, right? Like greater than this guy. What is subtract then so and I create this guy actually is very well known guy. Very well known guy. One greater than big for you that you okay. So if I want to find the result in the solution or no, Alex is I have the answer you say not okay, you say definitely. Oh yeah. So far, kind of understand the. It's quite it's quite fun. I think lots. This actually right. Like Yeah. But everyone really ends. And then when you do for me, they will also divide I guess this entire data structure is just how do you like you break the combination and try to combine if I have extra time, I'll talk about this is what I think the outside goes from the outer. I think I'll take a long time.
These are all the number from.
High priest.
Within this I need to be able to predict any rate. The idea so in biology,
I think it's just like different special dimensions.
I thought we actually one. Every number just this is like
Again, the more common
every number just twice except for one. Just ignore everything.
if you have certain problems, they use this kind of then people will just second their salary.
Yeah. I don't think unless you are like working. No, I don't need
Oh.
Yeah.
Because you have the same problem. I know like segment of system, but you didn't think I don't have two children. Oh, but they all sit there. Even though you bring in two children,
I mean, I would use I wish I could think. Yes. Okay, I mean the design kind of like generalize the idea of the value. If you are querying it, right, you're just going to propagate down the delete at aggregate and just need to propagate down so and since everything is the same word, everything will match the same word. And he changed this. Not now. Yeah, not here. Just for like past like few sessions. I never knew about
we don't use this shit.
Excessively, maybe not.
Okay, excessively actually, the 4K bioinformatics. What? The bioinformatics is just straight out of it. But you bring that like this,
How many slides I have left?
But now you only counted one.
These two are I won't do. Actually, everything onwards from here is bonus. Yeah, I just want to cover lazy propagation. Then the rest is just then I'll cover the problem maybe. Okay. Yeah, so okay, maybe let's get back into it. So where was I just now? Oh yeah. Just now I was showing the problem of what happens when what just now I was showing the problem of what happens when you don't actually push the children back, you don't push the updates into the children, right? Because just now what happened was, okay, I added the aggregate add into the sum. Then afterwards, I queried it again. So now I query 04. I query 04, then I return 18. But 18 is not the correct answer, right? Because I actually added 2 to everything in here already. So what this bug showed us was that we actually need to define how aggregate add is pushed down to children. When we apply aggregate add, we also need to take care to push the update down into its children. Does that make sense? So actually what we should have done is rather than 56, 0, like after we apply, we just set to 0. We also needed to push the 2 down to its children, right? Then now let's query 04 again. If we query 04 again, then okay, we go down here, then now we see that this aggregate add is actually here. We will apply it, then we'll return the answer. Does that make sense? The missing step here was pushing the aggregate add down to its children. Okay, so now this is the state of our segment tree. So now we do update 024. Okay, 02 still within our node, still very nice. Okay, let's do so now it's like this, right? 4. Okay. Now we do query 04. We query 04, we take 18, we add 2 in. Then what is this? This is 4, this will be 26. And then we push the update down into its children. Is this the correct way of pushing the update down its children? No, right? Instead what it should be is it should take into account what's already in the children, then it adds the aggregate add on top of it. So it should be like this instead. Correct? Did I screw something up? Query 04. Oh, sorry. Oh yeah, sorry, I added 4 to it. So what this showed us was, on top of defining how aggregate add should be pushed down to its children, we also need to define how an aggregate add is composed with another aggregate add. So, okay, the reason why I'm using all of these like a bit more abstract terms to describe this whole stuff when actually I should just be calling it like adding it or like pushing it down to its children, right? Is because in this case, I'm doing addition, but actually segment trees is a lot more general. It's a lot more like you can generalize it to use for a lot of other different types of operations. So it's more of like, rather than adding it, it's more of like composing an add with an add. Yeah, okay, anyways, that was a side point. Now, okay, yes. So we figured out that we need to define how aggregate add interacts with other aggregate adds. This part makes sense so far, right? So now let's call query 04. Okay, query 04. This is 26, and then this is 0. We query 04, we what was it supposed to show? Okay, we query 04, then we'll call sum on these two things. We call sum on these two things. We apply 6 to these two elements. It will get pushed to 6. It will get pushed to 6. This will get applied in. So this is plus 12. This is what? 7 plus 12 is 19. Then similarly for here, we apply 2 into this. So this will be plus 4 to this. This will become 15. Then the 2 will get pushed down to here and here. Then afterwards, now we return the sum here, which will be 19 plus 15. This is what? 34. Yeah. Okay. So now I return 34, right? Then now let me query 0 to 8 again. When I query 0 to 8, what happens? I return 56, right? But it's not 50. Eh? Yeah, it shouldn't be 56, right? Because is it 46? Wait, I query 04. 19 plus 15 is 34. Okay, sorry. Okay, this one was from the original update where I added 082 to everything.
That's 46.
That's 46. Oh. Am I stupid? Oh yeah, okay, sorry. But then on top of that, actually I did this update 024 earlier, right? So it shouldn't be 46. It should be something more than 46, right? So what happened here? What, like we're still leaking, we're still like missing updates all over the place. What's going on? Right? So it turns out that our missing problem was that when we did an update, we didn't push the answer back up. So what I mean by that is, okay, just now we did okay, let me think. What would be the best way to show this? Okay. Ignore whatever I did just now. Let me start on a fresh canvas. Let's say now I do update 024, right? 024. So now I query 024 will only update this part, right? Right. But now I query 08 again. And then I'll just return 30, right? Because this thing has nothing that has to be applied to it. But this is an issue. This is not what we want, right? Because we needed to apply the operation in there, but then we return 30. So what's the missing step? The missing step is that when we do an update, when we update something, we're not propagating all of the updates back up again. Right? So instead, what should have been done was that, okay, if we update a node, what we should have done is that we should have updated the parents as well. Right? And we need to propagate this answer all the way back up. Right? So if we aggregate added 4 to this node over here, what we should have done is, okay, we should have calculated, okay, how does this affect? So this plus 8 becomes 15. Then I go 4 here. Then I needed to recompute everything again. This becomes 26. Then this becomes 38. Does this make sense? Everyone follow me so far, right? Yeah. So which is the part that's a bit confusing.
Oh.
So now that we've considered like all of these considerations that we have to make, right, we can actually start thinking of how to actually write the update function for this, right? So we know that firstly, we need to think about how does aggregate add get applied to the sum. We also need to think about how aggregate add gets composed and with another aggregate add. If a parent calls an aggregate add that needs to be pushed down to its children, if its children already have an aggregate add, how does it interact, right? And we also need to consider about how to even push down the aggregate add to the children, right? These are all considerations that we've learned that we need to These are all considerations that we found out after working through the entire query, and we think about how, okay, if I have this aggregate add variable, how does it actually need to interact with everything, right? So far, make sense? And then at the same time, we also realized that we need to change a bit of our old code as well. When we call sum on a node, if there is an aggregate add, right, we actually need to apply aggregate add on the sum. Then afterwards, we need to push down the aggregate add to the two children node. Then we can continue calling sum as per normal, right? But these are all consequences that we've sort of derived as a result of actually going through this step of thinking how does this data structure actually work? How should this data structure actually work? Okay, and then now let's think about calling update on a node. So if let's say I want to call update on I don't know, what do I want to call update on? Okay, let's say I call update on 2 to 7, right? Update on 2 to 7. If I was breaking it up into the blocks like how I did just now, 0, 1, 2, 3, 4, 5, 6, 7. Like how I did just now for add, right? I wanted to pick like the minimum amount of blocks that I want to actually push the update into, correct? So in this case, if I update 2 to 7, it will be this range, and I only want to update these 2 blocks, right? Makes sense, right? Minimize the amount of updates I want to do, minimize the amount of blocks I want to use. Then, if that's the case, right, then there is also a similar recursive structure that we want to use, like for update as with sum, right? We start from the top. If this update doesn't affect this range, if this update doesn't affect this range, we don't give a shit. If this update fully contained within this range, then that's great already. We can just change the update accordingly. But if the range of the update intersects the range of the node itself, is too coarse. We need to actually break it down even further. So this is a similar recursive structure to the sum operation just now. But at the same time, Okay, so fully contained within the range, we compose the aggregate at. Fully disjoint, we don't give a shit. Then, if otherwise, we just break it down further. We call update left child, update right child. At the same time, we also, based off what we learned just now, where every time we do an update, we also need to recalculate the sum and push it back up. We actually need to recalculate the value of sum after calling update left child and update right child. Make sense? So this is the essence of how lazy propagation works. So I want to make an update to a range. Rather than updating every single element and pushing the updates upwards, I think about how I can actually update the block. I think about how this interacts with everything else, and then I change my code accordingly to fit. Right? So, okay. This was supposed to be a slide where I just step through everything again. So let's just do it for the sake of maybe I change this to update 3.2. Yeah. Okay. Update 0.82. Okay, very nice. Let's see. Okay, yeah. Then because there are no parents, I don't have to push this update back up again. Query 0.8. Okay, since I'm querying it, I apply this in. Then this is what? This is 56. Then I push the updates down to its children. Query 0.4, similar situation. Where, okay, I apply the update in. This is what? 2 plus 2 times 4. This is 26, right? How do I keep making this issue? Yeah, okay. Then I push the updates down again. Then update 0 to 3 to 2. This is 0, 1, 2, 3. Okay. So now 0 to 3 to 2, basically which blocks do we have to consider? We have to consider this block and this block, correct? So, God damn, okay. Hello. Yeah. Okay, so I have to compose the aggregate add into this. 4. I have to compose the aggregate add into this. Then what does this become actually? This becomes 2. Yeah. Then because I've changed these two nodes, right? Actually, I have to figure out how to propagate the answers back up again. Right? So what I actually need to do is that after I apply the aggregate add, I need to find the sum of this, which will actually force a what did I do? I call sum on this one, which will force the addition of the aggregate add in. 4 times 2, that's 8. This is 15. Then I push the 4 back down. I call the aggregate sum on this, which becomes 4. Then afterwards, I need to call the sum on this, right? What's going on now? Oh yeah, sorry. Oh yeah. Sorry, this will become 6, right? Oh, okay, sorry, my brain's not working. Well, basically you need to propagate it back up. This is the type of stuff where you need to implement it. You need to implement it, then you need to see like why is it buggy, then you kind of get a sense of what the logic actually is like. So now I claim that range update is log n. So similar argument to the sum. You think about what you're actually doing, you realize that you only do 4 operations at every level. So it's 4 times log n. That gives you log n overall. Then this is some other stuff which doesn't really matter. So we wanted some range query data structure, which gives us range queries in log n, point updates in log n, and now we have range updates in log n. So we have found a fantastic range query data structure. We no longer need an inverse, and instead what we need is that, okay, we just need to reason about how do we apply this operation to a block and all the different interactions that we have. We have found a fantastic range query data structure. Wow. After 1 hour and 30 minutes, we've covered segment trees with lazy propagation. Okay. So okay, I guess at this point, any questions, like any weird parts that you didn't really catch, you want me to repeat again?
When the last time you used it? Any setting? Never.
I used it for like one of the OAs, I think. Wait, because there was some like it's like if you wanted to do it like properly, which I guess is find some smart solution to do it, it's so bloody hard. But if you just throw a segment tree, it's so easy. Okay. Any questions? Okay. In the absence of questions, I'll go talk about a bit more. So okay. So just now we needed for the prefix sums we needed an inverse, right? But in this case, you realize we did not use the inverse at any point, right? It's just the operations. We just needed to add stuff together. So actually, this is an even more general data structure, right? Now this is like operations such as minimum queries, right? Range minimums, we can actually support with segment trees. Maximums we can also support. So all of these stuff we can now support it with segment trees. Ignore this. So yeah, now it's the bonus sections part. So this talk was prefix sums and segment trees. I actually have two more stuff, which is square root decomposition and sparse table. So in terms of actual like utility, I've literally never used this before. I've used this only once, right? But the idea is quite simple. I think I can actually get it across. So just now we had like let's say this is our array, right? And we want to do range queries. The idea of square root decomposition is this. Just now we broke it up into blocks of size, like we broke it up into like log2 blocks, right? We divide it in half, we divide it in half, divide it in half. What if instead of breaking it out into blocks of log2, I break it out into blocks of size square root n? Okay, sounds damn weird, but like bear with me for a second. Okay, so let's say each block is square root n. Each block is square root n, right? So yeah. How many of such blocks should there be? I have blocks that are of length square root n. The overall array is length n. So there should be n divided by square root n there should be square root n blocks of length square root n, right? Okay. Then if for every single block of size square root n, I calculate like the sum of it, of every single block. Each block is square root n, right? So each block is square root n. Then I have square root n of such blocks. How much computation do I do in total? N operations are right. Okay. So you might think, okay, why would I do something so weird, right? What's the point of doing this? But the thing is, doing this actually allows, because how do I put this? Okay. So if you break up each range query into this, right? You use the square root n blocks as much as possible. If it's fully contained, you use it. Otherwise, you add like you add like the stragglers on their own. So let's say I wanted to do an operation where I add all of this stuff, right? Assume that all of these are whole blocks. These are all square root n blocks that are fully contained, right? Then I still have some stuff on the side which is not fully contained within a block, right? I claim that adding everything up is all square root n. Right? Like literally whatever range you do, it will always be all square root n. Why is that the case? Let's think about it. Okay, so you break it out into the three portions, right? One is the stuff that's dangling on the left, one is the stuff that's dangling on the right. And then in the middle is all the big blocks, which are like they're fully contained blocks. How many big blocks are there? square root n. You've already computed them, right? So it's O1 to find their sums, right? Then to sum all of them out, it's okay. Then on the left side, how many of such things on the left can there be? Less than square root n. On the right side, square root n plus square root n plus square root n. You have square root n operations. So with this, like just breaking up the blocks into square root n, you get square root n operations, which is like it's like a who in their right mind would think about this, but it's cool lah. It's cool from like just looking at it algorithmically. Tell me how do I put my screen back?
I didn't do anything.
Yeah. And here. Okay. Yeah. Sure. Oh, sure. Yeah, let's just call it a day here because the rest are all just bonus questions. Basically, that's all of the stuff I wanted to cover. Yeah, sure. What's up?
No, I just say I need like questions, like questions or example questions.
I guess you should just. Okay. Just give me a second. Let me end it here. Okay, so that's more or less the entire presentation. I'll stop it here. I'll be here for some questions. See you guys. Okay.